Hello, this is Lazarus at telecomTech, where telecom and networking technologies are simply explained. Today we'll be simply explaining Layer 2 encapsulation, ARP, and framing. Now, in one of my previous videos, someone had requested that we go over the process by which a host prepares data to be sent on the wire, and how the encapsulation process takes place from Layer 3 to Layer 2. This includes the operation of ARP, or Address Resolution Protocol, as well as how Ethernet framing is managed and organized. So in this video, that's what we'll be looking at. So let's get right into it. Let's say we have this network here, and this host 1 is sending some data to host 3. Note that these two hosts are on the same network segment, the same broadcast domain, and they are within the same subnet. Here's our packet, with the source and destination IP addresses already in the IP header. Now, when encapsulation takes place, the Ethernet header must be populated with the appropriate source and destination MAC addresses. We know the source MAC address, which is that of our sending host, but we don't know the destination MAC address. To find out what it is, we must use what is known as ARP, or Address Resolution Protocol. Now at this point, we're in the process of encapsulation, encapsulating this IP packet into the frame, but the process pauses here in order to determine that destination MAC. Now ARP resolves the destination MAC address from the destination IP address. The first thing that the host does is look in its local ARP table. This is a construct within every network device that maintains a list of cached MAC address to IP address mappings. If the entry for the particular destination IP address exists, it will be taken from there, and the destination MAC address field in the Ethernet header will be populated, and the frame will be sent along its way. Now in our case, host 1 doesn't have the IP address of our destination in the ARP table, so it can't populate the destination address in the frame. So what does it do? It sends an ARP request to find out the MAC address that corresponds to the destination IP address. This is a broadcast message that is sent at layer 2 to all hosts on the segment. All hosts will receive it and will check the IP address that is being requested. All hosts will discard this ARP request except for the host to whom it belongs. That host will respond with an ARP reply containing its own MAC address. The sending host will receive this, place the destination MAC in the destination MAC address field, and will send the frame along its way. Now at the same time, the local ARP table of host 1 will be populated with the MAC address and IP address pairing, so that any future frames being sent to host 3 will not need to send out an ARP request again, but will get the destination MAC address from the entry in the ARP table. Now this ARP table is also known as an ARP cache. Now that frame will be sent to the switch, and the switch will use its MAC address table to determine the exit interface and will forward it accordingly. When the frame reaches the destination, it is decapsulated and the payload data is processed. Now, it's important to understand the difference between the ARP table and the MAC address table, as these may sometimes be confused. The ARP table is maintained by the source device, that is, the device generating the frames and sending them out. The switch here is not a source device, so it does not maintain an ARP table for the frames it serves. However, if the switch itself is the source of data, it will maintain an ARP table, but just for communications that take place with the switch as a source or destination device. For example, if you have this PC here and an administrator connects to the command line interface of the switch using SSH, for example, the switch will communicate with that host and will create an ARP table. Within it, there will be a correspondence of MAC addresses and IP addresses of the hosts with which it communicates. However, this is a completely different process than the MAC address table the switch maintains. The MAC address table is maintained by the switch for transient traffic. That is, for traffic that it simply receives, switches, and relays. Now, I mention this because this was a point of confusion for me when I was learning. So that's the ARP table versus the MAC address table. Okay, so that's how ARP works when you are communicating between two hosts on the same subnet. But what if we have a scenario like this one? In this case, host 1 with an IP address of 10.10.10.11 is sending a packet to host 4 with an IP address of 10.10.20.14, which is in a different subnet. In this case, does the sending host send an ARP request for the IP address of the destination? No. Remember, ARP is a layer 2 protocol with a layer 2 scope. That means that its scope will only reach the local broadcast domain or network segment. Host 4 here is in a completely different network segment. So what happens now? Well, when the time comes for this packet to be encapsulated into the frame, when we determine the destination MAC address, it doesn't make sense to try to find the MAC address of host 4 here because it's in a different subnet. It can't be reached at layer 2. But what can be reached and should be reached is the default gateway. Indeed, the default gateway is the next hop in the process. So the default gateway that has been configured within host 1 is the next hop to reach the destination. So the ARP request goes out for the MAC address that corresponds to the IP address of the default gateway. So we follow the same process, but this time not for the destination IP address, since it's in a different subnet, but for the address of the next hop, which is the default gateway. Now, I don't show it all here, but of course, we first look within the ARP cache of host 1, and if we don't find the mapping of the IP address of the default gateway in there, then we send the ARP request for the MAC address of the default gateway. Once we get the ARP response, we populate the destination MAC address of the frame header and send the frame along its way. We also populate the ARP cache of host 1 with the corresponding IP and MAC address pair for the default gateway. The destination MAC in the frame header is now the MAC address of the default gateway or the next hop. So once the default gateway receives the frame, it decapsulates it up to layer 2, checks the destination MAC address, sees that it is indeed for itself, and then it decapsulates up to layer 3. It looks at the destination IP address, puts it through its routing table, determines the next hop IP address and the exit interface, and prepares to encapsulate the packet once again into a new Ethernet frame to be sent out. Now, in this encapsulation process, the source MAC address is that of the exit interface of the router, while the destination MAC address must now be determined. And how do we do that? Well, we follow the same ARP process that we saw until now. I won't show it in detail here in the diagram, but what we need to do is to learn the MAC address of the very next hop. The routing table tells us that the destination IP in the IP header is on a network that's directly connected. So we know that the next hop IP must be that of the destination. So we check the local ARP table of the router to see if we have an entry. If we do, then we use that to populate the destination MAC address. If we don't, we send out an ARP request to determine the MAC address of this host here. Now, this host responds, the MAC address is placed in the destination field of the frame, and it is also used to populate the local ARP cache of the router. Finally, the switch now receives the frame, and it switches it to the appropriate port based on the destination MAC address of the intended host. The frame reaches the final host, is decapsulated, and the data is received and processed. And that's the whole process going from host 1 to host 4 via an intermediary router. Now, a couple of things I'd like to point out here. First, you can see that the source and destination IP addresses remain the same for the whole duration of the transmission. IP addresses at layer 3 provide end-to-end communication from host to host, and that's why those addresses remain unchanged. The source and destination MAC addresses, however, change at each hop. The ARP process must take place from host 1 to find the MAC address of the default gateway, and then when the router routes the packet, it must re-encapsulate it into a new Ethernet frame with a new source and destination MAC on this leg of the communication. All that takes place because layer 2 has a scope that corresponds only to a network segment or to the broadcast domain in question, and ARP only functions within that scope. So we see that the source and destination MAC addresses change from hop to hop, unlike the IP addresses, which remain the same throughout the communication. And finally, I'd also like to mention that the ARP table entries are not permanent. Much like the MAC address table, they have a timeout, which is typically on the order of several minutes to several hours. And that timeout is highly dependent on the operating system that's being used. On some systems, you can actually adjust that timeout. For Cisco devices like a router, the ARP cache is maintained for 4 hours or for 240 minutes, while a Windows PC can have a much shorter timeout on the order of 30 seconds to 2 minutes. So that's how encapsulation, ARP, and framing all work together at layer 2. For now, if you've watched all the way to the end, thank you. It tells me that you're not just looking for quick answers, you're actually trying to understand how networking works, and I really appreciate that. If you'd like to go deeper, you can visit my website at telecomTech.io, where I'm building structured network courses with hands-on labs, quizzes, and practical scenarios to help you really master these technologies. Feel free to check it out and join the newsletter so you can stay informed about new courses and content as they are released. You can find a link to all of that in the description below. I'm Lazarus at telecomTech. I hope this has been helpful for you, and I'd like to thank you for watching.